I am talking today. So I guess I introduce myself. I am Shotaro Makisumi from Colombia, and I'll be giving the second talk in the series on two realizations on equivariantization and de-equivariantization. So most of what I'll be talking about today is categorical language, but just a little bit motivation. We saw the K0 story last time in Pablo's talk. And the categorification in the end that we'll get to takes the form of triangulated equivalence between some category associated to G and another category associated to its Langland's dual G check. And on one side, let's say to G check, we'll have some category of coherent sheaves, or maybe derived, maybe equivariant. And on the other side, you'll have a category of constructible sheaves associated to some geometric object associated to G. Now, how do you define that kind of a functor? Well, you want to use some structures on the target category. So let me just start with an example. So let me assume throughout this talk that K is an algebraically closed field of characteristic 0. So for example, if I have a linear category, and A is a commutative K algebra, so what this means is I have an algebra map from A to the center of my category. So A acts functorially on every object and every Helm space in my category. In that case, it turns out, under suitable assumptions on my category, that I can actually upgrade that to the action of a monoidal category, the category of A modules, or quasi-coherent sheaves on spec A. The idea is, well, the A linear structure tells you how morphisms from A to itself should act. And then every module you try to build out of copies of A. So another name for this kind of structure is called a category over spec A. And today I want to
okay.
Yeah.
Ask a question. So
yes,
it's just basically by taking tensor products.
Yes, it's by taking tensor products. I'm just assuming C has suitable colimits or something so that I can do this. It's basically by taking tensor products. I'll say a little bit more in a bit. So yeah, I want to say more generally later today, what does it mean to have a linear structure for stack, not just spec A? So I want to really not worry so much about some of the assumptions on my categories and stacks throughout this talk. So sorry, but to any algebraic stack, there's an associated monoidal category of quasi-coherent sheaves on it. And then a category over the stack is just an action of this monoidal category. So you can phrase it in two different ways. First, you can say it's a monoidal functor from this monoidal category to the monoidal category of endofunctors of C. Or if you unwind that a little bit, you can say it's a bifunctor. So this tells you how a quasi-coherent sheaf acts on an arbitrary object of C. And this action, as usual, has to satisfy some conditions. There has to be an associator and unitor satisfying some compatibility. So, I mean, that's a definition, but we really want to understand it and try to make it a bit more manageable. So for instance, of special interest are when we consider category over a stack of the form point mod G, so BG, or spec A mod G. So in those cases, I'll say a bit more about what quasi-coherent sheaf on a stack means in a little bit. But in this case, you have rep G or G equivariant A modules as the category of quasi-coherent sheaves. And so I'm trying to define an action of these monoidal categories. So, for example, what's the data needed to define an action of rep G? And here I want to use a heuristic about objects on a quotient stack. So this is a heuristic that needs to be made precise, but it says that an object on BG is the same as an object on point together with a G action. So G equivariant objects on a point. For example, when objects are quasi-coherent sheaves, this tells you exactly that a quasi-coherent sheaf on a point mod G is, well, it's a quasi-coherent sheaf on a point, which is just a vector space, and it has an action of G. So well, you have to be a bit more careful in how you say this, but in the end, you get G representations on the left. And now I want to consider the case when objects are categories. So I expect some correspondence of the form a category over point mod G. Remember, that means a category with an action of the monoidal category rep G corresponds to a category over a point is just a category, or maybe K-linear category with a G action. Okay, so let's first do the case when G is a finite group. This is very nice and concrete. So I have to change my notation a little bit. I'm going to say now that rep G is the monoidal category of finite dimensional K representations of G. And so in this case, I want to give a more precise version of this correspondence I mentioned between a category with a G action and a category with a rep G action. So let's just think a little bit more carefully about what these actions mean. Associated to a finite group G, there are two monoidal categories. So of course we know rep G, but this other one, underlying G, is, I'm just viewing G as a monoidal category in the following way. Its objects are elements of G, and it only has identity morphisms. The monoidal structure is given by the multiplication in G. Let me define a G action on a category to just be a monoidal functor from underlying G to endomorphisms of C. So more concretely, that's saying to any object in underlying G, meaning any element, little g, I have an endofunctor fg of C. And then I give natural isomorphisms and compatibility. So for example, so I should really think of this endofunctor fg as the action of little g. And then I want the action of the identity to be naturally isomorphic to the identity functor. And acting by g followed by acting by h should be naturally isomorphic to acting by hg. The other kind of action is one I've already said. So rep G is a monoidal category, and then it makes sense to talk about an action of a monoidal category. So in the case of a finite group, here's one form of a precise correspondence. So you can find this theorem written in this 4-author paper, and it's very short, it's very readable, and they also say that it's a well-known theorem. So this states there are adjoint functors, or two functors if you would like, between K-linear categories with a G action and K-linear categories with rep G action, called equivariantization, going from left to right, and de-equivariantization, going from right to left. Let me denote these by these upper G and lower G. And moreover, if you restrict on both sides to Karubian, so idempotent complete categories, then this is actually a mutually, these equivariantization and de-equivariantization are actually mutually equivalent as two functors. So that means, for example, that if I start with a C, equivariantize, and then de-equivariantize that, there will be some natural isomorphism between that and the original category C that is compatible with the G action. So just as an example, I haven't told you how this works yet, but for example, if I take just a trivial action of my category G on finite dimensional vector spaces. So for every little g in G, my endofunctor f sub little g is just the identity functor. Then in that case, this construction will spit out the category of representations of G. So let's see how this works. Here's a definition. An equivariant object in C, a G equivariant object in C, is an object in C together with isomorphisms of this form. So remember, this f sub G was supposed to be the action of G. So you're saying after acting by G, it's isomorphic to the original object. And I actually fix an isomorphism. And this data is required to satisfy some natural compatibility. Then you can guess what a G equivariant morphism is. It's just a morphism of the underlying objects in C that commutes with all these isomorphisms U sub G. I define the equivariantization C upper G to just be the category of G equivariant objects and G equivariant morphisms. So you can already tell if you go back to the example that I mentioned. I have the trivial action of G on vector spaces. Then a G equivariant object is, well, it's a vector space together with, well, this is just a map from X to X in that case. So it's an isomorphism for every element G. And this compatibility is exactly giving you that it's a representation of G. So this two functor was supposed to be spitting out a category with a rep G action. So how does that work? Well, I want to define an action of the monoidal category rep G. So take some representation B, and I define its action on some G equivariant object in the following way. So it makes sense to just take this tensor product of V with X. It's just a direct sum of a bunch of copies of X, basically. And I give this new object the following G equivariant structure, this composition. So notice, if I take the example I mentioned, then this formula right here is saying element little g acts by tensor products of the actions on each factor. Okay, so this is exactly the way that rep G acts on itself. As another example, let's say you have a scheme X with a G action. And in that case, by pullback, G acts on quasi-coherent sheaves on X. And you can define G equivariant objects. And if you think about the definition, you see that the resulting category is exactly the category of G equivariant coherent sheaves on X. So how do you de-equivariantize? So for example, how can you somehow recover from rep G? Just knowing rep G as a category over it, as a module category over itself, can I recover a trivial action of G on vector spaces in some natural way. So here's how this works. Let's take the algebra of functions on G. So this is an algebra, but it also has a compatible action of G on the left and the right by translation. So using the left action, let's regard this as an algebra object in rep G. Now I want to go the other way around. So I'm starting with some category D with a rep G action. And whenever you have an action of a monoidal category and you have an algebra object in your monoidal category, it makes sense to define the notion of a module over this algebra in this module category. And I define de-equivariantization D sub G of D to just be the category of OG modules in D. So more explicitly, what is an OG module? Well, it's an object X in D together with some action morphism. And this action is, well, if you just think about the definition of a usual module, it should be OG acting on X to X, a morphism in D. And this makes sense because, so it makes sense to ask that this satisfies, for example, the associativity axiom, because OG is an algebra object. There is some morphism from OG tensor with itself to OG in your category rep G. And morphisms are, again, what you expect for a category of modules over OG.
So shall I think about it like this? So if I have a set X with a G action, I can multiply X by G and then take the quotient. And I recover my set X back, and I can also recover the G action.
Yes. Mm-hmm. So here I'm basically like tensoring with the regular representation. Yeah. So this also lets you recover the G action. So remember, de-equivariantization was supposed to go from a rep G module to a category with a G action. And this comes from, in this language, well, I haven't used the right G action on OG. And this is an action as an algebra object. So, well, if I have a OX module, then I can just change the action by pulling back under the right action on OG. So that gives you an action of G on the category D sub G. And the claim is that these two procedures are inverse equivalences, at least if you assume that the categories are idempotent complete. So for example, you should be able to start with vector spaces, first equivariantize to get to rep G, and then de-equivariantize. So I'm looking at OG modules in rep G. And there's a natural way of defining a functor from here to here. It's called induction. So I can take a vector space, and this direct sum is, well, first of all, it's canonically has a canonical G equivariant structure, but also because it's indexed by little g, so this is a G-graded vector space, there's an action of functions on G. So let me not say too much more about that, but from here you can use the fact that the category of vector space is Karoubian to try to define an inverse functor to this. And basically the same argument tells you in general, at least one way, if you take equivariantization followed by de-equivariantization, you recover the original category up to G-equivariant equivalence. Any questions so far? There's another perspective on this that might be useful. I don't want to say too much about this, but again, this can be found in the same reference, the 4-author paper that I mentioned. It's very short. I mean, the part that deals with this is very short. You can actually add a third leg to this correspondence and consider categories enriched in rep G. So that means that the Helm spaces can be viewed, the Helm spaces themselves have an action of G. Let me just do this example for equivariantization. In this example, I can factor equivariantization into 2 steps. In this intermediate category, I still look at G-equivariant objects, but the morphisms are going to be all morphisms in the starting category. I just ignore the G-equivariant structure that I just added. And then you know, of course, that this itself has a natural structure of a G representation. And you can recover the intertwiners, the morphisms in here, by saying, well, it's the G invariance of this Helm space. Maybe it's a bit early, but I'll take it's a good place to break. So let's meet back at 3:29.
So Tony asked a question in the chat. I guess like how do we recover just normal things on X if we're only allowed to consider G-equivariant things?
But you are not only considering G-equivariant things on X somehow, right? You are not restricted to a single set X. You consider all possible sets with G actions.
So I'm a little bit confused. Tony's question has to do with
I'm just trying to understand
Ivan's comment.
Ivan's intuition, like.
So we are talking about, we are in the setting where we are talking about actions of finite groups on sets. And then you want to kind of relate the equivariant categories, G-equivariant categories, to usual categories with G actions, like sheaves on categories of sheaves on various sets. And that's exactly what Makis or Greenfeld and everybody else's equivalence does in this sense, in this setting, right? Because on the level of sets or varieties or whatever, tensoring with O of G is just taking product with G. So that's the only thing that I'm saying. So it's kind of if you want to call it geometric shadow of a special case of this theorem. Does that make sense?
I agree that this is what the equivalence is doing. I just don't understand if this is supposed to make it seem intuitive or something, because.
Well, I think intuitive is a subjective thing.
So I'm going to rephrase this also later in terms of descent.
But maybe I'm misunderstanding this, but somehow I felt kind of Ivan, are you kind of Vanya? Are you kind of hinting at the fact, like from equivariant, like for example, cohomology? I kind of feel like this replacement of saying you replace x by g times x and then take the g quotient. It's kind of say you want to replace the action of g on x by some sort of like free action before you take the quotient, so that you can really don't lose any information, right? I don't know, or is this just like?
Well, I mean, kind of, but I'm just, you know, how do we kind of, I don't know, maybe this explanation generated more questions that it resolved, which may or may not be a good thing.
But coming back to Ben's question, I think, like Vanya, you were considering the diagonal action on g times x, right?
Well, I mod out the diagonal action.
Yeah, okay.
Which is diagonal for the left action on g and the only action on x, but then I also have a right action on g, which then gives me a g action on the quotient. So that's again what the theorem is telling you to do.
Yeah, my question wasn't a question. I was just asking whether that was Tony's confusion.
That's not my confusion. My confusion is to put myself in a psychological framework where I have x with a g action and I want to recover x with a g action. And I do it by multiplying by g and then dividing it by g. Like psychologically, I don't understand.
Well, my degree is in mathematics, not in psychology, so maybe I shouldn't answer this question.
So Jordy's latest comment seems helpful, and it's along the same direction as Toga was saying. We'll phrase things in a little bit in terms of the stack x mod g, but yeah, in this case, we can just talk about g cross x. Anyway, let me start the second part. So now I want to relate what I just talked about to the notion of a category over a stack. So in this part, I'm going to assume further that all my categories are k-linear abelian. And whenever I have the letter G, it's an affine algebraic group over K. And also, I'm taking the following material from Gates-Corey's short note, the notion of category over an algebraic stack. And again, I'm trying to brush under the rug some additional assumptions I have on my categories and stacks sometimes. So I apologize for that, but please see his notes for the precise statements. So here's the definition of an abelian category over a stack, same as what I mentioned in the introduction. And I also mentioned that when my stack is just an affine scheme, let's say spec A, then, well, this is basically the same thing for suitably, for suitable category C. This is the same thing as having an A linear structure on C. So here's how this works. If you have so you want to define an action starting with an A linear category of an arbitrary A module. If your module is just a direct sum of some copies, doesn't have to be finite, of A, then, well, so you know that a single copy of A acts by the identity because A is the monoidal unit. So you're forced to take this. Okay, and then given an arbitrary module, you can present it and take the corresponding presentation basically as the definition of this action. And then this will have some nice exactness properties. But as Ivan says, this is basically tensor product. So I want to go now in the direction of what is a sheaf of categories over a stack, as opposed to just a category over a stack. And to do that, I need to really understand pullbacks of categories just on affine schemes. So say I have a category C over spec A, so an A linear category, and I have a function, an algebra map from A to A prime. So map of spec in the other direction. And then I want to define a new category where the objects are the same as C, but objects are an object of C together with some action of A prime that extends the existing A action. So I'm not giving very much details, but the important thing is that this resulting category is universal among A prime linear categories admitting a functor from C. And the most important example here, if I take quasi-coherent sheaves, then it behaves in this nice way. So as a warm-up, before defining what a sheaf of categories over a stack is, let me say what a quasi-coherent sheaf on a stack is. Remember, a stack is, well, a scheme is determined by its points. For a stack, you generalize the set to be a groupoid. So now you allow a set where the elements have some automorphism groups. Then a quasi-coherent sheaf F on some stack Y is the following data. Well, I need to tell you what the pullback of this. So if I imagine that I have a morphism from an affine scheme to Y, then I should be able to define what is the pullback of F to S. And the result should be just a quasi-coherent sheaf on S. And I know what that means. So let me just call that this. I mean, this pullback Y star is not defined. It's just part of the definition of what a quasi-coherent sheaf on the stack Y is. And then I need all these pullbacks to be compatible. So, so here, Y1 and Y2 are morphisms from some test affine scheme to Y. And F is a morphism of affine schemes. But this might not necessarily commute. For example, if I take point mod G to be my stack, and point for S1 and S2, then there's a unique map here, but this unique map has automorphisms now. So for any such automorphism, I now want to write down some compatibility between these pullbacks. So this is an additional structure, and this has to satisfy some compatibility relations. So again, this example, the definition of point mod G is that the S points are G principal bundles on S. In particular, this groupoid contains the trivial bundle, whose automorphism group is just the S points of my group. So that means, as a part of the data of a quasi-coherent sheaf on point mod G, well, the pullback to a point is just a vector space, and then because of the compatibility relations, the pullback to any spec A has to be this tensor product. And now, because the automorphism group is G of A for spec A, now you have an action of the A points of G on this tensor product. And that's by definition a rational G representation. So of course, there's a priori more data in a quasi-coherent sheaf over point mod G. But in fact, this is enough info. And essentially, you're using, this is some sort of descent statement along the map from point to point mod G. So a quasi-coherent sheaf on point mod G is the same as after you pull back to a point already. This is just a vector space together with some descent data, and this is an equivalence. And you can actually rewrite this descent data in terms of this familiar coaction. So you get the other definition of a rational G representation. So I want to do a very similar thing with categories instead of quasi-coherent sheaves. A sheaf of categories, let me use this notation, SH, to remind myself that it's a sheaf over a stack Y is, well, for every affine scheme, now I want a category. And I want it to be a category over S. So that means if S is spec A, this is an A linear category. Now, if I have a morphism of affine schemes over Y, then now it makes sense to ask for a functor relating those categories. So this is the analogous of the compatibility relation, that compatibility isomorphism that we had in quasi-coherent sheaves. And so this is exactly the pullback of categories that we defined earlier for morphism of affine schemes. Now, because it's a category, you actually need one more piece of data. And all this has to satisfy compatibility relations. For example, a sheaf of categories over a point, one example is to just assign to any affine scheme its category of quasi-coherent sheaves. You might want to think of this as in the following way. A quasi-coherent sheaf is a sheaf of OX modules. To any space X, you have this nice sheaf of rings called OX, and it makes sense to consider modules over this ring OX. Now, what is the categorical upgrade of OX? Well, a categorical upgrade of a ring is a monoidal category. It's even commutative, so a symmetric monoidal category maybe. And here it is. This is the categorical upgrade. So because a category assigned to spec A has to be A linear, that's the same thing, remember, as having an action of quasi-coherent sheaves on spec A. Okay, so you might think of this definition as saying that it's you have a sheaf of quasi-coherent sheaves on X modules. Okay, now we run the same kind of argument as before. If I take my stack to be point mod G, then again, what is a sheaf of categories over this? Well, to a point, I have to assign just a plain K-linear category. And then to any pullback to an affine scheme, you have the A points of your group G acting. And again, by a version of descent in this context, you can show that this is enough data to recover your original sheaf. And you can, again, rewrite the descent data as something very analogous to the coaction for a rational G representation. Okay, so I have these two notions. A category over a stack is what I started with. And in the end, that's what I want if I want to define an action of some coherent category. I also have the notion of a sheaf of categories over a stack. Well, if I have the latter, if I have a sheaf of categories over Y, then it's easy to get out of that a category over Y. Okay? I just take as this category of global sections, so it's what you expect. It's compatible objects, blah, blah. And so from the definition of a quasi-coherent sheaf over Y, because it's defined in this similar kind of manner, you see that the result definitely has an action of quasi-coherent sheaves on Y. Now, under suitable assumptions, you can actually reverse this procedure. So for details, you can see the notes of gauge-scory that I referenced earlier. But here's how you go back very roughly. So I start with a category over Y. And to define a sheaf over Y, I have to specify for any affine scheme S over Y some S linear category. And I do that in a way that should remind you exactly of de-equivariantization. So I take a certain algebra object. It's a push forward of the structure sheaf of S down to Y. This can be considered as an algebra object in the monoidal category of quasi-coherent sheaves on Y. And then I set this category to just be modules over that. Okay, then there's more definitions, and you have to check that, well, under the suitable assumptions I didn't mention, this actually forms a sheaf. But the first example, if you take Y to be point mod G, then this construction exactly gives you the de-equivariantization that we saw earlier in the context of finite groups. So if I call my original category D, then let me now use a new notation, D sub De-eq. And this is exactly OG modules in my starting category. Now there's some difficulty here with the fact that OG is maybe you have to pass to in the objects to define this. And I'll say a little bit more about that in a bit, but let me ignore that for now. Again, let me just assume that all my categories are have suitable co-limits to handle that. So this tells you that this de-equivariantization condition is, you can interpret also as a fiber category. So I'm starting with some category with an action of ref G, and then to produce this pullback, I form this construction. Okay, so this is a bit more involved than what we had for finite groups. But in this way, we've, again, have some correspondence between categories with a G action and categories over the stack point mod G. So now let's ask a slightly harder question. What is a category over spec A mod G? So A is a commutative K algebra with a G action. So from this commutative diagram, you can pass through a commutative diagram like this. So let me just slowly explain this. This bottom row is exactly what we had on the previous page. So there's a correspondence passing from an object on point mod, a category on point mod G, to a category on point with a G action. You can do the exact same thing doing de-equivariantization by considering spec A to spec A mod G. You just spell out the same thing. You find that there's again a correspondence between a category over spec A mod G and a category over spec A with an A linear G action. And these two procedures, these two rows, actually commute with forgetting the A action. So that means that if I want to define a category over spec A mod G, then I can do it in 2 steps. First, I can specify a category over point mod G. And then I can de-equivariantize. On the de-equivariantization, I can give an A linear structure. So here it is in writing. The de-equivariantization principle states that a data of a category over spec A mod G is equivalent to, first of all, you have a category just over point mod G, so it's just a rep G module. And then you want a G-equivariant A linear structure on the de-equivariantization. Or equivalently, you can give an A action on these Helm spaces that are functorial in objects X and D. So this equivalently part takes a little bit explanation, but it's similar to the discussion we were having earlier. This de-equivariantization procedure actually produces a functor. You can start from any object X in D, and then you can take a free module over the algebra object. And this functor can actually be identified with just the forget the G action functor, in the case that D is the G equivariantization of some category C.
Sorry, what's in D? Maybe I missed it.
Oh yeah, sorry. So in D is the in the objects of D, right? So yeah, I should have said. So in this principle, I'm no longer requiring that D has arbitrary co-limits or something. So so this functions on OG is I mean, it's in general a really big thing, and so this object really only exists as an in the objects of D. Does that make sense?
So maybe, Maki, it's worth saying that at the moment you're kind of moving from, so before was Gatesby's language and now this is Roman's language.
Yeah. So let's do an example of this. I think this is really nice. Let's let GM act naturally on A1. And let's use this principle to write down what a category over A1 mod GM is. So this principle tells you, first of all, you have to define a rep GM module. But rep GM is freely generated by the natural module. So that data is the same thing as just giving a category D with an automorphism. Let's call it shift by 1. Okay, now I need to give, according to this principle, an action of the functions on A1, that's a polynomial ring, on this Helm space. But so I can unwind this. Functions on GM is Laurent polynomials. So that turns into this just a direct product of all the shifts of X. So to give an action of A, to give an action of this algebra that's GM equivariant is the same as giving a graded action of this polynomial ring on this Helm space, graded in a natural way. So it's the same thing as giving a natural transformation from the identity functor to 1. So we boil down something geometric into some kind of combinatorial data, just 2 pieces of data. And Jordy tells me it's a worthwhile exercise, and I unfortunately haven't had the time to work this out. But in terms of the data of the previous slide, you can try to work out what this category is for y in this diagram. Any questions?
Maybe just to add to the worthwhile exercise, if you haven't thought about what coherent sheaves are on this stack, then do that first.
Okay, so in the last few minutes, I want to try to say something towards the strategy that's carried out in Roman's paper. So not only does point mod G make an appearance, I guess I've switched from G check, which was in the original motivation part for two realizations, but to G. But you want to produce some category over the Lie algebra mod the adjoint action. So, and this is a version of a Tannakian formalism. So let me just review the group version very quickly. And this just states basically that you can recover a group G from its category representations. So here's how this works. If you have a representation V, then for any A algebra, the A points acts on the base change to A of this representation A. And this action satisfies this usual relation. So you can turn this into a definition of a kind of an automorphism of this functor, forgetful functor to vector spaces, followed by tensoring up to A. And something that acts with this equation is called a tensor automorphism. And one way of phrasing Tannakian reconstruction is that every tensor automorphism is actually given by the action of an element of G. So what about the Lie algebra? Well, you can do basically the same thing. So now this base change again acts functorially on my objects, but satisfies a different equation. And again, you can turn this into the definition of a tensor derivation. It's some endo-natural isomorphism, natural endo transformation of this functor. Okay, and the theorem says you can actually recover the Lie algebra again from tensor derivations. So now we get this chain of isomorphisms. This first isomorphism is the previous page. And then I can rewrite a tensor G as a K algebra homomorphism from functions on the Lie algebra G to A. And if I add a G action on my K algebra A, then you can trace through this action and see that on the right-hand side, I'm going to end up with a morphism of schemes from spec A mod G to the Lie algebra G mod the adjoint action G. So the upshot is that if I have a G equivariant tensor derivation on this functor, then as soon as you have a spec A mod G linear structure on a category, you can actually upgrade it to a structure over this stack. And this observation we will use in later talks on Archibald Bezirkovnikov and Roman's full two realizations paper. That's all I wanted to say for today. Any questions?
That's not really a question, but maybe at some, well, and I'm pretty sure it will be done at some point, but kind of. Usually when you produce a whole lot of this fancy language, it's good to explain how exactly it's going to be used. And why,
yes.
Why maybe not how exactly it's used, but why should we care about this language?
Yeah. Well, I was hoping to say just enough without, you know, giving you all the definitions of the categories, which we haven't done at all. But yeah,
somehow the point is that we are going to care about category of coherent sheaves and something like the Steinberg.
Yes,
and
that's right.
We are going to relate it to category of constructible sheaves and something like equivalent constructible sheaves and something like affine flag variety.
Flag variety. Mm-hmm. Yes.
And then we're making observations that the Steinberg is, you know, admits morphisms to Steinberg mod G, admits morphisms to, like, depending on what version you use, something like B mod.
Yes, I'm sure this will be explained in yeah, future talks. So
right, but somehow,
yes.
so yeah. It gives some structure. So yes. This morphisms. So how many morphisms do we have? We have 2 morphisms to B mod B, and the compositions of these 2 morphisms to G mod G agree. And kind of the point is to first translate this to a purely categorical language, which is what this talk is about to some extent. And,
yeah, so I agree. I mean, so let me just maybe say for the benefit of everyone else, what Ivan's saying here. So this category on the left is something like G-check equivariant coherent sheaves on the Steinberg. Yeah, and so instead of directly producing a functor like this, so that would be defining the structure of a category over the Steinberg here on this category. But you notice that the Steinberg, for example, admits, well, so I said, first of all, that it's actually G-check equivariant coherent sheaves on the Steinberg. So you can just forget everything except the G-check action. There's a map to point mod G-check. And first, you first start by defining the structure of just a category over point mod G-check here, BG-check here. And then you try to extend this step by step to larger and larger coherent categories. Is that okay for now?
Yeah, I mean, maybe it should be worth to point out that there are kind of, so that's the most adult version of this equivalence, but more baby versions were known before, and they kind of, you know, involve things like G-check coherent sheaves on the Springer resolution versus an appropriate thing on the constructible side, and then you somehow maybe it's a good idea to just say that well, I mean, you know, Steinberg is a fiber product, and so we want to kind of see the structure of modules over the fiber product. The structure of coherent sheaves over the fiber product in the constructible level.
Yeah. So I mean, so at the K0 level, this is already something that Pablo emphasized in his talk last week, that already in that proof, the anti-spherical module somehow plays a key role. And so, yeah, we'll first actually study that paper of Archibald Bezirkovnikov, which is about G-check equivariant coherent sheaves on the Springer resolution. It's a categorication of the anti-spherical module.
And also, it may be worth to point out that it's not unreasonable to expect that there will be other proofs of the two realization results appearing in some near future, which are maybe kind of more elementary.
What are you talking about?
Well, I mean, there is this work of Bezirkovnikov, Richard Ryder.
Yes.
Which should somehow do this from the Sorgiev theoretic perspective.
I have a bunch of questions, Mackie.
Yeah.
Back to the stuff at the beginning of the talk with equivariantization, de-equivariantization.
Yes.
I probably should really read this paper by the four authors, though I never have. You described how everything works for a finite group.
Yes.
Does that paper do things for other groups?
I think they only do finite groups, but they do upgrades of this to tensor categories. Like, but by tensor category, I guess they mean like rigid.
Rigid, yeah, that you don't want.
Yeah.
Okay. And the second question was, why does the characteristic zero function?
Yeah. So I think that so I told you where Karoubian is used. It was if you go from C to C upper G, C lower G, and to show that equivalence is use Karoubian already. So I think the other direction uses well it uses that the rep G is semi-simple. But I think the basic idea should be you want the regular representation to contain all the simples as a direct summand.
How much can that be fixed?
That's a good question. I don't know. So I would like to understand this too, if anybody in the audience knows.
Can you repeat the question, Mackie?
Yeah, so how much of this, just for finite groups already, how much of this correspondence works if K is a positive characteristic, if rep G is not semi-simple?
I think it's all okay. No, isn't? Wait. Let's see. Or you have to put maybe you have to change the category on one side. Let me remember. Let me think.
My next question, by the way, was going to be, well, at the end of this talk, you explained that there's also Tannakian formalism for Lie algebras, so there should be a version of this for Lie algebras too. Since it's infinitesimal, this should be an action. An action of a Lie algebra should fix all the objects, but should have an action of the Lie algebra on the morphisms.
Interesting.
So like when you go to that slide where you've got three things, where there's that thing in the middle, the
Yeah.
category, that certainly works pretty easily. So in this thing, you can certainly define what it means to be a k-linear category with a rep G action where G is the algebra. That makes perfect sense. You can certainly define what a rep G enriched category is when G is a Lie algebra. I guess there's no real definition of that upper left corner, though. But this under your Tannakian stuff, this is supposed to be what kind of sheaves on what kind of space?
I'm sorry, what?
Yeah, I'm just trying to unravel all this, right? Like,
yeah. So you're asking like, so this on this side, I'm thinking of something over point mod G, and this is over point. Is that what you mean?
Yeah, that's right. That's right. And so now I'm asking, what if G is the Lie algebra? Just replace capital G with macfrac G and mathfrac G in this whole statement. So a k-linear category with a rep little g action, is this like sheaves over some kind of, is this sheaves over some kind of stack?
I think you could think of it as a quotient stack by a formal group.
By a formal group.
Yeah.
And then the thing on the left-hand side would be some kind of weird formally equivariant objects.
Ben, I don't quite understand. So if you if you care about finite dimensional representation of a simple algebra,
I don't care about finite dimensional representations.
I care about all representations.
Finite dimensional representations, Ivan. Like Verma modules, co-Verma modules.
Well, I mean, it does get even crazier than that.
Yes, I know. But I mean, all this stuff is very formal, and I don't see anything in anything you've said that says these vector spaces have to be finite dimensional. I mean, you've been doing quasi-coherent everywhere.
But when we talk about group, don't we care about rational representations? Because we are sort of, we are sort of doing algebraic geometry, and in algebraic geometry, it's difficult to care about other representations.
I'm not sure I buy that. I mean, weren't we doing, like, this category rep G we're talking about includes infinite dimensional representations.
But they're rational, no?
Yes.
So somehow.
Okay, but.
Well, it's kind of obviously you shouldn't take my whatever statements I make about algebraic geometry very seriously. But I've heard that there is some issue with talking about arbitrary representations.
Right. Okay.
You want to do algebraic geometry.
I don't know what the right statement is for Lie algebras then. What sort of rational representations one should restrict to.
But for the stuff you're thinking about, so you're saying you already have these two?
Well, yeah. I mean, right. Sure. Well, I mean, really, what you have is the upper left corner. Really. Really, what you have is the upper left corner. Maybe I'll put it that way.
Capital G is replaced by a Lie algebra now?
Yes.
No, but what do you mean by left corner, upper left corner then?
So I mean that you have a category where all Hom spaces have an action of a given Lie algebra, and composition is satisfies your Leibniz rule.
It sounds like this, no?
No, but that's different.
No.
I think you're working in a dual a dual setting.
Yes, you're right.
Where instead of being enriched in rep G, you're thinking of G enriched category, isn't it?
Sorry. Mackey's right. I think I'm at the bottom.
No, you're not at the you're not rep. you're not thinking of red G enriched. I think you're really thinking of G enriched category, which is also something that exists.
What does that mean? G is
you can think of a category enriched. No, sorry. Okay, sorry. I was thinking of something that makes sense for me for abelian group. No, here there's no choice. Sorry, only one. I mean, the top left, I think, is not. You might be able to, as Tony was saying, you might be able to. I mean, the algebras are equivalent to formal groups, so you might be able to have a top left version with a formal group by replacing groups by formal groups, and then formal groups you go to Lie algebra.
Okay, so somebody who actually knows algebraic geometry should do this.
Well, so somebody who knows Denise Gainsbourg can just ask him.
Fair enough.
But you're saying this stuff is going to be useful for what you're thinking about.
I'm saying that all the categories you're talking about are this for SL2. If you've been to any of the talks I've given recently, all the Hecke category, affine Hecke category, and type A have actions of the Lie algebra SL2.
I mean, this language. Yeah, I don't know. I mean, this is all language, right? At some point, I'm not really sure how you want to use this.
No, it can be useful because you're changing the object you're working with. I mean, that's what's also interesting. It's like working with a graded object instead of, or working just with objects. I mean, the home spaces, everything changes. So I think what Ben is saying is will work, but it's because you're going to end up with a group with only 1 point. So if you skip your scalars, you won't see anything. It's only you would have to extend to something like k of epsilon mod epsilon square. And that might be enough even, but so you would have your original category, and together with extra structure on the category, when you extend scalar from k to k of epsilon mod epsilon square, there you would have an action of the group that you derive from your Lie algebra, from the k of epsilon mod epsilon square points of your group scheme, of your formal group scheme.
So the geometric way to put this Lie algebra action would be to take this on this category would be to take the Steinberg and put some extra capital SL2 structure on the formal scheme that you get by having k epsilon mod epsilon squared, something like that.
I'm sorry, I'm lost. But what I'm saying is simpler. It's just somehow going from you have a notion of automorphisms of anything, and then you have a notion of infinitesimal automorphism, and how do you make sense of that? Various ways to make sense of that. And one way to say that it has to do with, I mean, you can talk of derivations, or you can say this is an action on your object where it extends scalar from k to k of epsilon mod epsilon square. Okay, so people must have used that somewhere, derivation action on categories.
I'll shut up now.
Anything else we want to discuss? Any questions?
Are there any examples that come up where the kind of A is not, or spec A is not really affine? You know what I mean?
Yeah, so that will in fact come up in our series of talks later, because so as Ivan was saying, the side is the Steinberg, and so as one step towards that, we're going to be considering the Springer resolution. So we'll have to really, yeah, we'll have to do this kind of thing where the stack is the Springer resolution mod G check.
And in order to approach those situations, we essentially use the thing that Vanya already said. Like, so for example, to make a category linear over G mod B, we say, oh, there's this thing that's almost affine called G mod U, space affine space living over it. And to make it linear over G mod B is the same thing as making it T equivariant linear over G mod U. And that's close enough to be affine to be able to use this equivariantization, de-equivariantization.
Right.
Okay, so I take it that's sufficient silence to say this is it.